This is a video about the structure and behavior of a ring and about the ring behavior calculator. It is a supplement to a journey through computation, natural and human. Now, the ring that we're going to talk about is a ring of 4 linked oscillation networks, each with a computation in it. Now, the first component of that ring network that we're interested in is the individual oscillation network. Individual oscillation network has 2 components. The first is the wavefront interaction flow path, which is shown here, and the second is the bubble closure flow path, which is highlighted here. Now you notice that the oscillation network is a composition of these 2 paths. Now the second component we're interested in is the wavefront interaction path for the ring as a whole, and that's here. And you'll notice that this is a composition of the wavefront interaction paths for all of the oscillation networks. All right. The third component we're interested in is the bubble closure flow path for the ring as a whole. And this path is a catenation of all of these, the bubble closure flow paths of each individual oscillation network. Now, wavefronts flow through the wavefront interaction flow path to the right. Bubbles flow through the bubble closure flow path to the left. You'll notice that as the wavefronts flow through the wavefront interaction network, that they do not flow through the bubble closure behaviors. And as the bubbles flow through the bubble closure network, they do not flow through the interaction computation behaviors. And we have 2 distinct flow networks, and those 2 distinct flow networks intersect by sharing all-of behaviors. Okay, so what we have here is 2 counterflowing intersecting flow networks. The first metric of ring behavior is the slowest oscillation network period, and that is all of the delays around the slowest oscillation network. The second metric is the wavefront population period, which is the time it takes all of the wavefronts in the ring to flow through the slowest oscillation network. And that is the number of wavefronts in the ring times the slowest oscillation network period. And conversely, the bubble population period is the time it takes the population of bubbles in the ring to flow through the slowest oscillation network. And that is the number of bubbles in the ring times the slowest oscillation network period. Then we have the wavefront rejoin latency period, which is the total delay of the ring wavefront interaction path, which is the interaction path all the way around the ring. And then the bubble rejoin latency period is the total delay of the ring bubble closure path. Now the wavefront path is how long it takes a wavefront to flow all the way around the ring. The bubble rejoin latency period is how long it takes a bubble to flow all the way around the ring. A ring network has 3 behavior modes: wavefront limited behavior, bubble limited behavior, and delay limited behavior. If the wavefront population period is less than the wavefront rejoin period, the lead wavefront never overtakes the trailing wavefront of the wavefront population. The slowest oscillation network in the bubbles will wait on wavefronts, which do not wait on anything, and the wavefronts determine the throughput of the ring, which is the wavefront population over the wavefront rejoin period. Conversely, if the bubble population period is less than the bubble rejoin period, then the lead bubble never overtakes the trailing bubble of the bubble population. And the slowest oscillation network in wavefronts will wait on bubbles, which do not wait on anything. And the bubbles determine the throughput of the ring, which is the bubble population over the bubble rejoin period. Now, if there is a slowest oscillation network, then both the population periods can be greater than their respective rejoin periods. So the ring is neither wavefront limited nor bubble limited. Both wavefronts and bubbles will overtake their respective populations at the slowest oscillation network. The wavefronts and the bubbles wait on the delay of the slowest oscillation network, which does not wait on anything. And the delay determines the throughput of the ring, which is one wavefront per period of slowest oscillation network. Now you'll notice the ratio up here of the wavefront period, population period to the rejoin period is less than 1 when we're wavefront limited, and the bubble population period is less than the bubble rejoin period is less than 1 when we're bubble limited, and these ratios will figure into the calculator, which we'll talk about next. This is the ring behavior calculator for a ring with 30 oscillation networks. The oscillation networks are characterized in this section over here, and the networks are numbered from 1 to 30, and each network has the delay for the wavefront interaction path and the delay for the bubble closure path, and the sum of those delays, which is the oscillation network period. And in this case, all of these delays are equal. All of the periods are 600, to begin with here. Down here, we have the number of oscillation networks in the ring. We have the sum of the wavefront latency rejoin periods, which is the wavefront latency period. And we have the sum of the bubble closure delay periods, which is the bubble latency rejoin period. And here we have the slowest oscillation network period, right? So there's a search through here. We'll just quickly here, we'll show that, okay? And so this now 1200, right? So we'll get the slowest oscillation network. Up here is the behavior calculation of the ring. For the different populations of waves, right? So this is the population of waves, 2, 4, 6, 8, and so forth. They're populated in pairs of waves. This is the column of the bubble population of the ring, and the number of bubbles in the ring is the number of wavefronts in the ring subtracted from the number of oscillation networks in the ring. This is the wavefront period for the population. So this is the wavefront population times the slowest oscillation network. And these times are in nanoseconds. You'll notice that these times are in picoseconds and these times are in nanoseconds. And this is the wavefront rejoin latency period, which is this divided by 1,000, right? So that makes this nanoseconds. This is the bubble population period, which is the number of bubbles times the slowest oscillation network. And this is the bubble latency rejoin period, which is this divided by 1,000. Now this is the throughput, right? There's a calculation here that takes all of these numbers and calculates the throughput and also determines the behavior mode. Okay, and this is in gigahertz. But we multiply the gigahertz by 10 to get a reasonable graph down here. If we didn't multiply the throughput by 10, everything would be all jumbled up and it would be hard to read. So the multiplication by 10 is to make a reasonably looking graph. Okay, so now the calculation determines what behavior mode we're in. Okay, and these are all wavefront limited and these are all bubble limited. And it can be delay limited and it can be perfectly balanced, and there's a couple others. This column is the wave ratio. Now we mentioned before the population period minus the population period over the latency period is less than 1, then we're wavefront limited. Okay, and with the bubbles, if the population period of the bubbles is less than the latency period of the bubbles, then we're bubble limited. And these are those ratios, right? So here we're wavefront limited, and then we become not wavefront limited. Here we're not bubble limited, and here we become bubble limited. Now this column just gives us the reference line for 1. Okay, and the graph down here, the red line is the throughput line, and you can see the throughput is increasing up to 778, 778, and then it decreases as we become bubble limited. And because all of the delays in the oscillation networks are the same, this is symmetrical. Now, if you remember in the demonstration, as we added wavefronts to the ring network, the throughput increased to a peak, and then as we kept adding waves, it became bubble limited and the throughput decreased. And that's what this line is showing. Now, these lines, this is the wavefront ratio, and this line is the bubble ratio. This is a bar that we can move around. And now we'll notice that the wavefront ratio is crossing 1 and the bubble ratio is crossing 1 at the same point. And what that means is that everything to the left of this bar is wavefront limited, right? Because this line is less than 1. And everything to the right of this bar is bubble limited because this line is less than 1. Okay, let's look at the effects of delays on the performance of the ring. First of all, we'll change all of the wavefront interaction path delays. We'll make it 600 in all the oscillation networks. And you can see the bubble closure path delay is 300. And the graph, it still has a peak, but now it is asymmetric. And there are more wavefronts on the wavefront limited side now because the wavefront latency rejoin period is so long that more wavefronts can get through the slowest oscillation network. So now if we move our bar over here, we can see that the ratio lines still intersect at the 1 line, and everything to the left of the bar is wavefront limited. Everything to the right of the bar is bubble limited. And if we look up here in the behavior list, we'll see that we're wavefront limited for up to 18 wavefronts. And then there's a perfect balance. And then we're bubble limited. And this peak is a perfect balance. And we'll talk about that again later. Now let's do it the other way. Make the bubble closure longer than the wavefront interaction path delay, and we'll see it's asymmetric in the other direction. Now the bubble latency rejoin period is so long that lots of bubbles can get through the slowest oscillation network before a bubble can get around the ring. Okay, well, let's go back to that and let's look at a single slowest oscillation network. So we'll put a delay in one oscillation network in the wavefront interaction path. And this is what we see. Okay, so the graph has a flat area now. And if you remember before that the throughput with the delay was 1 wavefront per delay period. And that's what we're seeing here. So this is the delay period. And no matter how many wavefronts we have across this area, the delay is constant. It's always the delay period. Now on this side of the delay period, there's some wavefront limited behavior. On this side, there's some bubble limited behavior. And the delay limited behavior has a plateau. We call that the delay limited plateau. Okay, so now we'll take our bar and we'll look at, now here's where the bubble ratio line crosses 1. So everything to the right of this is bubble limited. Everything to the left of it is not bubble limited, right? So it happens to be delay limited and wavefront limited. So if we go over here and look at where the wavefront ratio line crosses 1, everything to the left of that is wavefront limited, and everything to the right is not wavefront limited. Okay, so in between where it's not wavefront limited and where it's not bubble limited, it's delay limited. And up here, we can see the behavior modes. You know, we have wavefront limited. The first 3 are wavefront limited. And then at this corner, we have a perfect balance. And then we have a bunch of delay limited, and it all has the same throughput. And then we have 3 populations that are bubble limited. Now we're going to make the slowest oscillation network a little bit slower by adding a larger delay onto the wavefront interaction delay. And you'll notice that the delay plateau is much lower and it's much bigger. So now there are only 3 wavefronts. The first 3 wavefronts are wavefront limited, and only the last 2 populations are bubble limited. Now, up here, there's two that are wave limited, and there's a perfect balance, and then there's all the delay limited populations across the delay plateau, and then the last 2 are bubble limited populations. Now, we have a perfect balance here, and that is on the left edge of the plateau, or the wavefront limited edge of the delay plateau. And I'm going to show you this perfect balance behavior with the demonstration network. Okay, so we'll get this demonstration started here. We'll add 2 more wavefront pairs to the ring. Now there's 3 wavefront pairs flowing around the ring. And now I'm going to set this delay at 66. Looks like it's going to be 65. Okay, now watch this node, and we'll give all the behavior, and we'll give the wavefronts a little time to find their stride flowing around the ring and through the delay. You notice that the wavefront is waiting here for the closure. Now you'll notice that the wavefront and the closure are arriving just in time. Okay, and the wavefront flows straight through to the delay. It flows through the delay and then around the ring. So now what this means is that the wavefront population period is the same as the wavefront rejoin period, right? And the ratio is 1. And it also means that we're operating at the left of the delay plateau in the graph, right? And we're getting the optimal throughput. We'll talk about the optimal throughput in a bit. Now, if this delay is a little shorter, the closure will get there quicker than the wavefront. If it's a little longer, the wavefront will get there quicker than the closure. So this is the particular delay that is operating at the left edge of the delay plateau. So along the delay plateau, there's more wavefronts, added wavefronts. So we'll add a couple of wavefront pairs. Let's see, so we've added 2 wavefront pairs, and we'll give the wavefronts a little time to restride themselves. Now you notice that the wavefront is always waiting at this node. And furthermore, the wavefronts are backing up. This wavefront is waiting. It's waiting here. It's waiting here, right? The wavefronts are free-flowing up to this point, right? Because we added 4 more wavefronts, 2 wavefront pairs. Now those 2 wavefronts are lining up behind the delay, waiting to get through the delay. And we are no longer at the left edge of the delay plateau. We're in the middle of the delay plateau. So let's return to the calculator and review what we just watched. So here's the graph. And as we add wavefront pairs, the throughput increases to the 3rd wavefront pair. And then as we add wavefront pairs after that, the throughput does not increase, but each new wavefront pair increases the transition behavior in the ring, increases the energy cost, if you like. So this corner of the delay plateau is an optimal behavior point for the ring, right? So we get the optimal throughput for the minimal energy cost. Now, if we look up here, we can see that in the numbers. The wave population period and the wave latency rejoin period are the same. And what that means is that the wave ratio is 1. It's perfectly balanced here. We saw this in the demonstration with the closure and the wavefront arriving just in time at the olive behavior just before the delay. So this optimal behavior point corresponds to the wave ratio of 1. Now, not all delays result in a wave ratio of 1 or a perfect balance. So we'll do 1390 here, a delay of 1390, and we'll notice that it's not perfectly balanced, but now it's delay limited. If we do 1370, it's no longer perfectly balanced, but now it's wave limited. But this is still a 1.0, but these are not the same. We just didn't get to the decimal points here. So if we do 1350, we can see that this is now not 1. Okay, so given that optimal behavior occurs at this, there is an optimal behavior point, and the optimal behavior point is when the wave ratio is 1, or as close as you can get to 1. Given your delays and your wavefronts and so forth, your optimal ring behavior is as close as you can get to the wave ratio of 1. Now, all this other stuff that says, it's delay limited, we can characterize all this, but these are not optimal efficiency behaviors, especially in bubble limited. A few words about the behavior calculator. It is a spreadsheet. It's available in both numbers format and Excel format. And the file has other calculators. There's the one for 32 oscillation network rings, so you can see a really symmetric ring that has a single peak, right? This is 16 wavefronts and 16 bubbles at the peak. There's a 31 oscillation network ring, which illustrates the behavior of an asymmetric ring. And then there's a 30 oscillation network ring, which we've been working with, which corresponds to the demonstration network ring of 30 oscillation networks. Here's the 14 wavefront 16 bubble peak and the 16 wavefront 14 bubble peak. And there is a 4 oscillation network ring and a 3 oscillation network ring. And these are the ones you'll most commonly encounter in practical circumstances. And we'll talk about these in a later presentation. Now, the spreadsheet files are downloadable from carlfant.net.